Welcome to this week's first lecture in EE557. In the last lecture, we have seen the conditional PDFs for linear Gaussian systems and in general for linear systems. In this lecture, we are going to start to see unconditional PDFs, and then we are going to start investigating their properties as k goes to infinity, which are going to be called asymptotic properties. So the first thing is going to be to write actually what our system is. So I have xk plus 1 is equal to axk plus buk plus gwk. So this is our system equation. And I have the output equation, yk is equal to cxk plus hvk. Remember, in this chapter of the book, we are considering deterministic inputs. And that means that UK is selected deterministically. Okay? And we can write the distributions of the initial condition. X0 is normal with X0 bar mean and sigma 0 covariance. And I have WK normal with 0 mean and Q covariance, and VK is normal with VK as the argument of the distribution, and I have the 0 mean and covariance R. So we also assume that X0, W0, W1 going until infinity, and I have V0, V1 going until infinity are independent. Okay? So we had these assumptions on the system. And under these assumptions, we can calculate, if the system has Markov property, and we can calculate these transition probabilities. So we have seen so far the following distributions, xk, uk. This was the one-step transition PDF. And I had P of xk plus m given xk, uk from k to k plus m minus 1. Okay. M-step transition PDF, and we had seen so far the conditional output PDF, which is called the likelihood. And here these are, as you see, all conditional PDFs. Now I can start to calculate what the unconditional PDFs of the state would be. Remember, we have written so far this transition expression. I can write that here again, xk plus m is equal to a to the m, xk, plus I from 0 to I have m minus 1, a to the m minus 1 minus I, and I have b uk plus I, and plus I have I from 0 to m minus 1, a to the m minus 1 minus I, and g, and I have w, k plus I. This is the m-step transition function of the state. And starting from that point, I can actually try to obtain the marginal distribution of the state, unconditional marginal distribution of the state. So we are asking here the question, so we have already found these, and I'm asking the question of what is Pxk, the marginal distribution of the state. In order to be able to write such a conditional distribution, I need to write such an unconditional distribution. I need to write xk in terms of the basic random variables. So I want to write xk in terms of x0, w0, w1, going until wk minus 1. And I can actually do it from the m-step transition expression here. How can I do that? I can here, in that expression, I can set k equals to 0. I want the transition function from k equals to 0 to k equals to k. Okay? So I want m to be equal to k. Okay? I am making these settings in that transition function. In that case, you see that k plus m is nothing but k with these selections. In general, I don't show these as equalities, just set m to k, set k to 0, and then k plus m would be equal to k in that case. So instead of k plus m, I write k. So that gives me xk, that is equal to, I have a to the m is k, a to the k times x0, plus I have I from 0 to m is k, k minus 1, a to the k minus 1 minus I, b, and I have u, k plus I. K is set to be equal to 0, so I have just ui here. So you see here that this expression involves u from 0 to k minus 1. And I have plus I from 0 to k minus 1, a to the k minus 1 minus I. Everything will be here the same until g, and I have wi. Okay? So this is our expression for xk in terms of the basic random variables, x0 and w0s here. And ui's are deterministic. As a result, the only randomness here are coming from x0, and I have w from 0 to k minus 1. Okay? So now I have to calculate this distribution. So we see that we have these basic random variables, x0, w from 0 to k minus 1. They are independent in the Gaussian. That actually means that these random variables, x0 from w0 to wk minus 1, they are also jointly Gaussian. And I have here a linear function of jointly Gaussian random variables plus some deterministic constant here. That means that my result is going to be a linear or an affine function of jointly Gaussian random variables. That means that xk is going to be Gaussian. So what this means is that I can calculate xk's distribution by calculating its mean and its covariance. Okay? Let us calculate the mean of the xk. This is going to be xk bar. So I have xk bar. That is equal to expected value of xk. This is the definition of xk bar, and that is going to be, let us take expected values of all sides. Expected value can be distributed over these summations, so I can take the expected value of each term. A to the k is deterministic and linear. It can get outside the expectation, and I can write here ak times expected value of x0, which is x0 bar, and the expected values of these quantities. These are all deterministic. That means that they're going to get outside of expectation directly. So I have I from 0 to k minus 1, a to the k minus 1 minus I have b ui here. And then I will take the expected value of each one of these process noise terms. And I know that these are again linear in wi, and I will take the expected value of wi directly. That is going to be equal to 0, which means that all of these terms are going to disappear here. So this is the expected value of xk. Now I can calculate the covariance of xk. In order to be able to do that, I will subtract the mean of xk from xk itself. That is going to be xk minus xk bar, which is going to be, I have this ak x0, and I will subtract these terms from xk. So if I subtract ak x0 bar from ak x0, I will get a to the k x0 minus x0 bar. And that input terms, they are deterministic, and these terms are going to cancel those. So I will not have any input term here in the xk minus xk bar. And finally, I will have the process noise terms. They will come into this error term directly. I from 0 to k minus 1, a to the k minus 1 minus I, and I have g wi. So then I have to calculate the covariance of xk, which is by definition expected value of xk minus xk bar, xk minus xk bar transpose. Okay? So now look at these terms. This is x0 minus x0 bar. Expected value of this term is 0. And these are some w terms. And the expected value of them are also equal to 0. Okay? So here, instead of wi, I can write wi minus 0. Wi minus its expected value. Okay? So now think that you multiply these terms with their selves, with their transposes. So I'm going to, let us do it in a long way. So I have ak, x0 minus x0 bar, plus I have I from 0, k minus 1, a to the k minus 1 minus I, g, wi minus 0. So I have these terms times these terms transposed, okay? So let us take the transpose here, x0 minus x0 bar transpose, and I have a transpose k, or a k transpose here, okay? Plus the summation, I from 0 to k minus 1, this is going to be wi minus 0 transpose, and I have g transpose, and I have a to the k minus 1 minus I transpose. Okay? So maybe I should also close the parentheses of brackets of expected value. Now think that you are multiplying these terms one by one. So when I multiply these two terms, you see that it's going to be ak times x0 minus x0 bar times x0 minus x0 bar transpose times ak transpose. So we see that this ak and ak transpose can get outside the expectation, and I only have to take the expectation of x0 minus x0 bar times its transpose. But that is nothing but the definition of sigma 0. Okay? So I have here ak, x0 minus x0 bar, ak times, I have sigma k, ak transpose here. Now let us think that I multiply this term with the process noise terms. I know that x0 is independent with wi. That means that I can actually separate that expectation into two, and that is going to be expectation of x0 minus x0 bar times expectation of wi minus 0. Both of those expectations are 0, so I know that the cross terms will not bring me anything. Similarly, these cross terms will not bring me anything. And I have here two summations, and I have, let us do it in the long way again. So I have here I from 0 to k minus 1. So here I am multiplying two summations, and if I use the same index for both of them, it's not going to be good. I need to use another index for the second one. So I have j from 0 to k minus 1. And I have k minus 1 minus I, g wi. I will not write wi minus 0 here. Or let us write it. I don't care now, however long it is. So this is going to be wj now. And I have g transpose, a to the k minus 1 minus j. And I have transpose here. And I have to, of course, take this expected value of this thing. So expected value can always enter into a summation. So I will write this. So you see that I have double summations here. And now what I can do is the following. ak, sigma k, ak transpose, plus I from 0 to k minus 1, j from 0 to k minus 1, okay? And I can take these matrices outside the expectation, AK minus 1 minus I, G, and I will take expected value Wi minus 0, Wj minus 0 here, transpose, and I have G transpose, A to the K minus 1 minus J transpose. Okay? So I'm really doing this in a long way. At the end, I will tell you, of course, the short way to do this is that to realize that this term is independent with all of the process noise terms, and all of the process noise terms are independent. That means that when I take the covariance of this term, then I need to write some of the individual covariances of these terms. And the covariance of this term is going to be AK times sigma k times, maybe I'm doing everything wrong here. This is not sigma k, this is sigma 0. I'm sorry for this. So I have sigma 0 here. The covariance of this thing is AK, sigma 0 AK transpose. And the covariances of these terms are going to be AK minus 1 minus I, G, times the covariance of Wi, Q, times G transpose A to the K minus 1 minus I. Okay? So I'm really doing this in a long way. So what is this expected value? So I see here that we are taking the expected value of Wi times Wj transpose. I know that if I is not equal to j, these noise terms are independent from each other. Okay? That means that I can distribute the expectation as expected value of Wi times expected value of Wj transpose, which is 0, which are both equal to 0. So when I is not equal to j, this is going to be equal to 0. So I'm going to have here delta ij, Kronecker delta, which is 1 if I is equal to j, which is 0 if I is not equal to j. And in that case, what happens when I have I equals to j? In that case, I would have Wi times Wi transpose expected value, which is going to be just Q. Okay? So we see that these expectations are equal to 0 if I is not equal to j, and they are equal to Q if I is equal to j. Okay? Now I can actually use this fact as follows: A to the K sigma 0 A to the K transpose plus both of these summations are going to turn into a single summation, because when I changes from 0 to k minus 1, I will keep only the j value which is equal to I. Okay? That means that I can substitute j equals to I in the argument of these summations, and when j is equal to I can replace this expected value with q. So I have I from 0 to k minus 1, a to the k minus 1 minus I times g times q times g transpose times a to the k minus 1 minus I transpose. Okay? So this is our sigma k. Okay? But you see here that this is nothing but the individual summation of the individual covariances of each of these k terms here. Okay? So I have the individual covariance of this term would be ak times sigma 0 times ak transpose, and this is not passing through the correct way, so it's going to be something like this. And the individual covariance of these terms would be a to the k minus 1 minus I times g times the covariance of this times the transpose of this matrix. Okay? So we have found sigma k as well. Now I can actually write the distribution of xk, which is P of xk. So I see here this P of xk is normal and its argument is xk, its mean is going to be xk bar. Let us write it. A to the k, x0 bar, plus I from 0 to k minus 1, a to the k minus 1 minus I, b ui. This is the mean. And finally, I have the covariance, a to the k, sigma 0, a to the k transpose, plus that term. I from 0 to k minus 1, a to the k minus 1 minus I, g, q, g transpose, a to the k minus 1 minus I transpose. Okay? And I need to close the parentheses of the Gaussian here. So you see that we could find the unconditional PDF of the state using the properties of Gaussian random variables. So now we are going to ask a similar question. What is going to happen to the unconditional distribution of the output? I'm asking a very, very similar question. So you see that the output and the state are given like this. xk is a function of, I have erased it. So xk is actually a function of x0 from w0 to wk minus 1. And when I look at yk, I also include here the effect of the measurement noise, vk. Okay? So it would be nice actually if I could use the results that I have found already in calculating P of yk. So the thing that you can do is that yk, in this case, is also a linear or affine function of jointly Gaussian random variables or random vectors. So that means that yk is also going to be Gaussian, and that also means that if I find the mean of yk and if I find the covariance of yk, then I'm done. Because in that, a Gaussian distribution can only be represented using its mean and covariance, and if I find the unconditional mean of yk and unconditional covariance of yk, then I am done. Okay? Let us calculate the unconditional mean of yk. Y bar k is expected value of yk. I will just use this expression here. So you see that if I take the expected value of both of these terms, the first term expected value will be c times xk bar, plus expected value of hvk is going to be h times 0. That means that this term is going to be 0. Okay? So I don't really have to write it. That means that the expected value of yk is c times xk bar. Let us calculate yk minus yk bar. In this case, it would be c times xk minus c times xk bar. So this is c times xk minus xk bar. Okay? Plus h vk. So we see here that yk is composed of this error term. Sometimes we are going to call this as error. So this term is composed of two terms, and these two terms are independent from each other. Why is that? Because we see that xk minus xk bar, we have already calculated it here. It is a linear combination of x0 and v0 from 0 to k minus 1. And I know that vk is independent from all of those random variables. That means that these two terms are actually independent from each other, which means that if I try to calculate the covariance, let us call this sigma ky, and that is going to be expected value yk minus yk bar and yk minus yk bar transpose. This is going to be the covariance of these two terms, summation of the covariances of these two terms, and that is going to be nothing but c times sigma k times c transpose plus covariance of this term, H times R times H transpose. Okay, this is my output covariance, unconditional output covariance, and this is unconditional output mean. Let me leave this. So I have. So now let us write the unconditional output distribution. It's normal in terms of yk. The mean is yk bar and the covariance is sigma k y. And if I write these mean and covariance terms, this is yk. C times xk bar is this. C times ak x0 bar plus I from 0 to k minus 1 b ui. And that is my mean. And the covariance is going to be C times sigma k times C transpose. So I have C times a to the k, sigma 0, a to the k transpose, plus I from 0 to k minus 1. I have a to the k minus 1 minus I, gq, g transpose, a to the k minus 1 minus I transpose. I would have C transpose plus H, R, H transpose, and close the Gaussian parentheses. So this is the marginal unconditional distribution of the output in our stochastic linear system. So now we're ready to calculate some cross covariances, and we are going to calculate the following covariance. Cross covariance of xk plus m and xk. Let us try to calculate this. When we ask for a cross covariance, what we have to do is to calculate this. So we are going to call this as sigma k plus m, comma, I have k. This is going to be defined as the cross covariance of these terms. Expected value xk plus m minus xk plus m bar times xk minus xk bar transpose. This is the cross covariance that we would like to calculate. So we already know what xk bar is, so we know what xk minus xk bar is. Let us write it once more. Xk minus xk bar was given as xk minus, you need to remember here the xk expression. So in that case, I have a to the k, x0 minus x0 bar. Sorry, I really do not have to even write this. So I'm going to instead do the following. So I will just write the mean of this expression. This is the marginal distribution, and this is the m-step transition function. Let us take the expected value of this expression, and that is going to give me the following. Xk plus m bar is equal to a to the m xk bar plus, these are deterministic terms, they are going to remain as they are, and I have m minus 1 minus I b uk plus I. So these are going to remain like this, and the expected value of all the process noise terms are 0. So you see that this is the m-step transition function for the mean, okay, mean of xk. Now let me calculate xk plus m minus xk plus m bar. So it is xk plus m minus xk plus m bar is going to be given the right-hand side here minus these. All right? So I have here a to the m, xk minus xk bar, and these input terms are going to be cancelled when I subtract xk plus m bar from xk plus m, and the process noise terms will remain. I from 0 to m minus 1, a to the m minus 1 minus I, g, w, k plus I. Okay? Now what I have to do in order to be able to calculate this expected value is to multiply this error term, k plus mth error, with xk minus xk bar transpose from the right. Okay? Let us try to do it. So I have sigma k plus m, k, is nothing but expected value of these terms, and I'm going to multiply them from the right by this xk minus xk bar transpose. And these are going to be expected value of a to the m, xk minus xk bar times this xk minus xk bar transpose. This is the first term, plus I can write the other ones. So I have these terms multiplied by xk minus xk bar transpose from the right. Expectation can always enter into a summation. A to the m minus 1 minus I, g, and I will write the expected value now, wk plus I, and I have xk minus xk bar transpose. Okay? So now you see that this a to the m can get outside the expectation, and I will take the expectation of the rest, which is sigma k. Okay? So k plus m, k is equal to a to the m times sigma k, and then I will calculate these expected values. But you see that xk was only a function of x0 and w0 to wk minus 1. And I here have wk for I equals to 0, wk plus 1, wk plus 2, etc. So I see that these noise terms should all be independent from these xk terms. That means that this expectation can be separated into two, expected value of wk plus I times expected value of xk minus xk bar transpose. And both of those expectations are 0. That means that these terms will not bring us anything in the end. So this is our final expression. So this cross covariance tells us something very important. Suppose that a to the m goes to 0 as m goes to infinity. Okay? Suppose a to the m goes to 0 as m goes to infinity. In that case, for large m, this cross covariance will be approximately 0. Okay? What does that mean? That means that the cross correlation between xk and its future value, xk plus m, would go to 0 as the distance between them gets larger and larger. That means that the system has some way of forgetting. Okay? It forgets its previous values so that its future values would become uncorrelated from its past values as time goes, as the distance between those values in time increases. Okay? So it is a very, very important property. And we are going to see when a to the m would go to 0 as m goes to infinity. So we are going to define a condition of a stability of a matrix. And in that case, we are going to call the A matrix stable if and only if all of its eigenvalues are strictly inside the unit circle in the complex plane. Remember, eigenvalues are always complex quantities. So if the matrix is not symmetric, eigenvalues can be complex. And saying that eigenvalues are between -1 and 1 would not make any sense, because in general, in order to give an interval or specify an interval for eigenvalues, is implicitly assuming that the eigenvalues are real. But if A matrix can have complex eigenvalues, that type of interval information would not make any sense. We are going to say the A matrix to be stable if and only if it has all of its eigenvalues in the unit circle in the complex plane. So if the magnitude of the eigenvalues are always strictly smaller than 1, and we're going to show that if the matrix A has such a condition, then A to the m would go to 0 as m goes to infinity. That is going to be a form of forgetting in the system. The system will forget its past as the time goes by. So these were the cross covariance values. And the next thing that we're going to do is to find some recursive expressions for sigma k and xk bar. Let us try to do it. We have found what xk bar is, and we know also what sigma k is, but we are going to now obtain some recursive expressions for them. Sometimes working with recursive expressions might be easier. Let us say that recursive expressions for xk bar and sigma k. These recursive expressions can really be obtained in a much easy way from these recursive expressions here. And an alternative way is to look at this xk bar. Let us write xk plus 1 bar, and we can try to write xk plus 1 bar in terms of xk bar, and etc. Okay? But this is one way, but it would deal with these summations and the other summations in sigma k. Instead, we are first going to obtain this from these recursive expressions. Let us take the expected value of the state equation here. In that case, it's going to be xk plus 1 bar is equal to A times xk bar plus B times UK is deterministic, so it remains here like this, and WK expectation is 0. So this is our recursive expression for the mean of the state. Okay? So we see that the mean evolves deterministically with the input UK. Okay? So here the mean is not affected by the amount of process noise at all. And here, if you look at these covariance formulas are also independent from the deterministic inputs. So you see that into the covariances, because UKs are always deterministic in our system definition here, it does not enter into any covariance expression at all. Okay? It only appears in the mean formulas. And let us calculate xk plus 1 minus xk plus 1 bar. In that case, that is going to be A times xk minus xk bar, and BUKs will cancel, and I would have GWK. Okay? So now I will take the covariance, I will multiply this thing with its transpose, and I will take the expected value, and that is going to give me sigma k plus 1. And these are again independent terms here, and as a result I can calculate the covariance of the sum as the sum of the covariances, and that gives me A times sigma k times A transpose plus G Q G transpose. Okay? So this is a recursive expression for the covariance of the state. Okay? As I told you here, I can actually obtain similar expressions using the final formulas for xk bar and sigma k. How can I do this? So I have here xk bar formula. So I just write xk plus 1 bar. Okay? That is, according to this formula, I have a to the k plus 1 x0 bar plus I from 0 to k. I'm substituting k plus 1 instead of k here. So this is k minus I b ui. Okay? So now let me take a parenthesis here. If I take a parenthesis, maybe before that I will separate the k term from the summation. A to the k plus 1 times x0 bar plus I from 0 to k minus 1. I have a to the k minus I bui plus the k term. I see that if I is equal to k, I would get a to the 0, which means that I have not a summation anymore. We see that here the k term is going to be just b times uk. Okay? So now what I can do is take a parenthesis in these terms. So I have, in a parenthesis, I have a to the k, x0 bar, plus I from 0 to k minus 1, a to the k minus 1 minus I, bui, and I have buk. But you see here that this is nothing but xk bar. It is this thing, okay? So that means that xk plus 1 bar is a times xk bar plus buk. Okay? So we get the same formula, as you see. So you can either use these final formulas that we have found in order to obtain recursions, or you can just use these recursive expressions and take their expected value and take their covariance to write the recursive formulas. So that finishes the expected values and the covariances and the distributions. Now the thing that we are going to see is what happens in a non-Gaussian but linear system. This is linear non-Gaussian case. In this case, I have the same state equation and same output equation. And input is deterministic as well. But instead of having these x0, wk and vk as Gaussian random variables, we might have just different distributions than Gaussian distribution for them. Okay? And I can leave the distribution unspecified, so that I can know that they are non-Gaussian, but I can leave the distribution unspecified, but I can give you just the means and the covariances. Okay? So let us say that expected value, so this is x0 bar, this is expected value of x0, and sigma 0 is expected, or let us write covariance of x0. Okay? Maybe I should write them in the other directions. So I can specify only the expected value and the covariance. Similarly, for the WK, I can write expected value of WK is 0, and covariance of WK is equal to Q. And I can write expected value of VK is equal to 0, and covariance of VK is equal to R. Okay? And I can leave the distribution unspecified. The distribution can be anything non-Gaussian. So here, we can say that all of the expected value and the covariance expressions that we have found so far, they did not use the Gaussianity property of the process noise, measurement noise, or the initial condition. Okay? The formulas related to expected values or covariances so that we have calculated so far, they did not use the fact that these random variables or the random vectors were Gaussian. Okay? They only used the fact that the mean of x0 is this, covariance is this, and I have the mean and covariance of the noise terms as specified here. Okay? We did not use in calculating the expected values the Gaussianity property of these random vectors. As a result, all of the expected value and the covariance formulas that we have found so far is valid for a linear and non-Gaussian system as well, as long as these conditions are satisfied. Of course, I need to also say that x0, w0, w1, v0, v1 are independent. So we have independence assumption, and we specify the means and covariances of these random variables, and we can claim that a linear non-Gaussian system would also have the same expected values and the same covariances as those we have calculated for the linear Gaussian case. Okay? So we can write the mean and covariance formulas are the same as the linear Gaussian case. But the distributions, the conditional distributions or the unconditional distributions that we have found, of course they are going to be different for linear non-Gaussian case. Okay? And in that case, finding the distributions, even the conditional ones, the conditional ones are usually much easier than unconditional ones, finding those distributions. But the distributions, of course, would be different than the Gaussian distributions that we have found for these variables. Okay? The densities will no longer be Gaussian in general. Okay? So the means and covariances that we calculate, they will not be able to represent the densities, the transition densities, or the unconditional densities that we have found anymore. Okay? They will be different densities, and they will require they might require additional parameters than mean and covariance for their representation. Okay? So this actually completes the part of the chapter that we are trying to cover. It is the properties of properties of stochastic linear systems. And in the next lecture, we are going to start investigating what happens to this mean and to this covariance. Especially, we are not going to be able to say much about the mean as k goes to infinity, because you see that this mean is dependent on this deterministic input. Without specifying the input, we will not know where that state is going to go as time k goes to infinity. But you see that the covariance is not dependent on the specific input values, but the covariance recursion is only dependent on the noise gain and the process noise covariance here. So we will be able to say something about the value of this covariance as k goes to infinity if some conditions are satisfied. And this condition that is going to ensure that this sigma k is going to converge to a constant value is going to be the stability of the A matrix. If the A matrix is stable, if all of its eigenvalues are in the unit circle, then we will see that the covariance of the state is going to converge to a constant value. What does that mean? So we have a state. So suppose that our state is one-dimensional. So this is my state space. So the distribution of x0 is going to be a Gaussian like this. Sometimes, if, for example, A is not stable, this covariance, this is sigma 0, I can call this small sigma 0, the variance here. This is normal with x0 bar and covariance sigma 0 or variance sigma 0. So if A is not stable, we are going to see that sometimes this covariance is going to get larger and larger. The mean, of course, is going to change depending on the input. So this is x0 bar, this is x1 bar, and x1 bar is going to depend on the input value. The covariance sigma 0 is going to get larger when it goes to sigma 1. And furthermore, if I increase the time, then we will see that this covariance is going to get larger and larger. So the covariance is going to diverge to infinity sometimes if A is not actually a stable matrix. And in that case, what happens? The state is going to become more and more uncertain. Okay? So the process noise is going to make the state more and more uncertain as time goes to infinity. But when A is stable, when the matrix A is stable, we are going to see that this covariance is going to converge to a constant value. Okay? That means that although these uncertainties would change in time for small k values, they might get larger, they might get smaller, depending on the initial value, we will see that they are going to converge to a constant value. That means that the state, as time k goes to infinity, its uncertainty, its amount of uncertainty will be bounded. Okay? State is going to converge to a Gaussian variable with constant variance as time goes to infinity. Okay? We are going to make a distinction between these two cases. We are going to see that when A is stable, then we will always have a stationary covariance for the stochastic process xk, and that is also going to mean that the output would also have a stationary covariance. So we will see that this xk process, if uk is, for example, constant, when A is stable, it's going to converge to a stationary Gaussian process, meaning that the mean of the process, it's just first order stationarity, but we can always check the second order, third order stationarities as well. But we will only see that if A is stable, and if, for example, U is constant, in that case, the state is going to become a first order stationary random process, meaning that its mean is going to be constant as time k goes to infinity, the asymptotic stationarity, and the covariance of the state is going to be constant. All right? So this is in some way important, because if k goes to infinity, if I know that the process is going into a stationary process, then that actually gives us a connection between the things that we will learn in this course and the things that you have learned in other courses. For example, if you are coming from, if you have taken a statistical signal processing course before, then you might have seen the filter called Wiener filter. Wiener filter is an optimal filter for stationary processes, meaning that in the calculation of the Wiener filter, you always use these autocorrelations, the covariance functions, etc. They are actually statistics of stationary processes. But in our case, this xk is in general not a stationary process. Its mean is changing, as you see. The mean is changing with u. If I change u, then the mean of xk is going to change. Similarly, if A is not a stable matrix, we are going to see that the covariance of the process will also change. That means that in general, xk is not a stationary random process. Its properties, mean and covariance, for example, its density properties are going to be changing in time. That means that the type of filters like Wiener filter would not be applicable for such a process, because that process is not stationary, and that means that you cannot calculate its autocorrelation function, autocorrelation matrix, etc. Okay? And that means that you cannot calculate a Wiener filter for filtering such a sequence, because Wiener filter assumes that the process underlying your outputs would be stationary. Okay? But here we are going to see that if A is a stable matrix, the mean and covariance, especially the covariance, is going to converge to a constant value, and this process is going to converge to a stationary random process. That means that asymptotically, our xk and yk will be stationary processes, which is going to mean that Wiener filter theory would be applicable as k goes to infinity. Okay? We're going to see that for non-stationary processes like this, we will not be able to obtain a Wiener filter, but we will define something called a Kalman filter. So Kalman filter is the generalization of Wiener filter to non-stationary processes. Okay? And we might see that, I don't know, I have not actually extracted notes from that part of the book, but when I try to teach you the Kalman filter, I will talk about the fact that if the process is asymptotically stationary, then the Kalman filter that we design for such an asymptotically stationary process is going to converge to a Wiener filter as time k goes to infinity. It is going to be a time invariant filter as time goes to infinity. So Kalman filter is in general a time varying filter because of the non-stationarity of the process, but we're going to see that if A is stable, then Kalman filter is going to turn into, as time goes to infinity, it's going to go to a time invariant filter, and the time invariant filter that we're going to converge to is going to be the Wiener filter itself. So my comments here, like Wiener filter, stationarity, etc., they are not in the, for example, first order stationarity, second order stationarity. They are not in the content of this course. So if you did not understand what I'm talking about here, it really does not matter. So it is just that I wanted to make some connection between the statistical signal processing theory and the theory that we're going to see here. If you are not familiar with the Wiener filter or the definition of the stationarity of a stochastic process, it really does not matter. They are not under the content of this course. So it doesn't matter if you did not understand those comments of mine. So this completes this lecture. In the next lecture, as I told you, we're going to go into the asymptotic properties of this state and possibly the output, but we are going to be mainly concerned about the state, and we are going to use some examples, and we're also going to try to give and prove some theorems, but it's going to be for the next time. That's all for this lecture. Thank you very much for watching.